So here we are now, just about halfway through the course, and we're going to start our discussion of carboxylic acids and esters. Of course, we've already mentioned carboxylic acids. They're the oxidation product of aldehydes, and we'll get to know them a little better here in this chapter. In this first lecture on chapter 16, we'll focus on the carboxylic acids, and obviously the esters will come later on. Okay, so let's start by defining carboxylic acids. A carboxylic acid contains a hydroxyl group, the OH group there that we associate with alcohols, but it's also attached to a carboxyl group, the carbonyl group. There is C double bond O. So we have the carbonyl, and that same carbon of the carbonyl is also attached to a hydroxyl group, and then typically another carbon group. It could be as simple as a hydrogen in the case of formic acid, but typically we'll have another carbon group. Another name for formic acid, of course, the IUPAC name is methanoic acid, and we'll deal with that idea of the IUPAC versus the common names. Again, it's going to be a problem here as it has been in the past. We see some other acids down there. Acetic acid would be our 2-carbon common name for the 2-carbon carboxylic acid. Of course, IUPAC name would be ethanoic acid. Stearic acid we'll talk about again when we talk about lipids because it's a fatty acid involved in the formation of fats and oils. And then finally, benzoic acid is an aromatic acid, and that should be clear in terms of coming right off of the benzene ring, so therefore the benzoic acid name. Okay, there it is already. We're looking at table 16.1 here, which has the IUPAC and common names of selected carboxylic acids. So there's our simplest carboxylic acid, methanoic acid, the 1-carbon carboxylic acid, much more commonly known by its common name of formic acid. Again, if you know your Latin, formic acid has the root of being has ant as its root, so it's an acid that is associated with ants from the ancient world, and therefore that common name persists today. Ethanoic acid, again more commonly known as acetic acid, and just like we've seen acetaldehyde, when we have that 2-carbon group, that acid prefix for the common name tends to be more commonly used than the ethan prefix for a 2-carbon group. Propanoic acid is commonly known as propionic acid, which is confusing that they're similar but not quite the same, so be careful with that one in particular. And then finally, another similar set, butanoic acid, is our IUPAC name for the 4-carbon carboxylic acid, whereas butyric acid is its more common name, and we'll see that it's an acid associated with butter when we talk about lipids in an upcoming chapter. So I'm the first to admit that the common names are particularly prevalent for the carboxylic acids, but we'll go ahead and learn the IUPAC naming rules because those are what we should be moving toward. So the name of the carboxylic acid of benzene, for instance, is benzoic acid. If we're looking at the carbon in the carbonyl group, it's bonded to carbon 1 on the benzene ring. This is the highest priority group yet. It's higher priority than the alcohols or the aldehydes or ketones. It's a very highly oxidized group, and it gets a lot of priority here in organic chemistry as a result. The ring is numbered to give the lowest possible numbers for any substituent, so we may be going clockwise or counterclockwise depending on what gives us the lowest sum of the substituent numbers. And then finally, for common names rather, the prefixes ortho, meta, and para may be used to show the position, but in IUPAC we should be using the numbers, so 1, 4 as opposed to para when we're dealing with IUPAC versus common names. All right, and here we see the common prefixes in use as well as the IUPAC names. So benzoic acid itself, we don't have to worry about any prefixes or numbers because that carbon 1 is necessarily the carbon to which the carboxyl group is bonded. In the case of our second image there in the middle, we have 4-aminobenzoic acid would be its IUPAC name. Para-aminobenzoic acid would be a common name, and then PABA, P-A-B-A, would be the very common abbreviation for that. It used to be in lots of products, sunscreens and other medical preparations, but then people got a little concerned and you started to see PABA free, just like more recently with things like plasticizers used in bottles, bisphenol A, BPA, and now everything's BPA free. There was some indication that there could be some issues with it, and so therefore manufacturers moved away from it to please the public. But again, sometimes it's more concern than necessarily hard facts as to what's going on chemically speaking. As we look at our last compound there, that's 3,4-dichlorobenzoic acid. We could also name that as meta-dichlorobenzoic acid if we were going to use the common name. But like I said, let's try to stick with IUPAC names because that's where we're trying to move chemistry, even though these common names do persist. Since the common names are so prevalent, let's talk a little bit about them, especially with the smaller carboxylic acids. So many of these small ones are still named by their common names, including those prefixes like we talked about. So form for 1 carbon, acid for 2, propion for 3, and butyr for 4. And then we'll get to pent and things get more normal after that. When we use these common names, we also will use Greek letters, alpha, beta, gamma, to indicate the carbons adjacent to that carboxyl group. So the carboxyl group itself, if you're ever really deep into chemistry, you may see it as referred to as the ipsius carbon. It's carbon number 1 in the IUPAC naming scheme. The carbon next to it, carbon 2, is known as the alpha carbon, and then carbon 3 would be beta, carbon 4 would be gamma, so on and so forth. You may have seen a lot of information and a lot of publicity about alpha hydroxy acids. These were a big thing for skincare in the last several years now. Again, it's just using that common naming scheme to say that there's a hydroxyl group, an OH group, on the alpha carbon, and that does seem to help remove dead layers of skin, and it was a big deal for the skin industry, but I'm sure they're on to the next big fad by now. Obviously, I don't keep up with it. My skin's probably not great, but again, I don't spend a lot of money either trying to make it look good. Looking at some properties of these common names for acids, formic acid, as I mentioned earlier, formis meaning ant in Latin, so formic acid, a red ant sting, contains formic acid that irritates the skin. Again, if it's just one red ant that stings you, hopefully it's not too irritating, but if you should get stung by a group of them, it is quite irritating and quite unpleasant, and hopefully it's nothing anyone listening out there ever experiences. Let's focus now on our guide to naming carboxylic acids. Of course, this is the IUPAC guide. We would first identify the longest carbon chain, replace that E ending from the corresponding alkane with the oic space acid ending. Okay, notice it's 2 words for carboxylic acids. Second, we'd give the location and name of each substituent by counting the carboxyl carbon as carbon number 1. It's the highest priority we encounter in the course, so it's always going to be carbon 1, unless, as we saw already, it happens to be bonded to a benzene ring. Then we consider the carbon that's bonded to that carboxyl carbon, that's a carbon member of the ring, as carbon 1. But other than that, the carboxyl carbon itself would be carbon number 1 in terms of naming. Okay, so let's practice a little bit here. We've got 2 structures, and our task is to give the IUPAC and common name for each carboxylic acid. So we see A, we have a straight chain. It's actually a branched alkane. There is a substituent there. And then B is an aromatic carboxylic acid with a chlorose group. So let's see how we name these things. So first, we'll analyze the problem. We notice that we have for the first A there, the only functional group is the carboxylic acid group. For B, we have the carboxylic acid group, an aromatic ring, and a chloro group. But in either case, the carboxylic acid is the highest priority group, so we change the E from the alkane name to oic acid, and then count from carbon 1 of the carboxylic acid for the straight chain form to account for any substituents, and the name would be an alkanic acid. Sorry about that. Alkanic acid would be the scheme for the naming there. Okay, so step 1 there, we're looking at the longest carbon chain, and so for A, the single longest chain that includes that carboxyl group is 4 carbons long, so it is a butanoic acid. For B, we're not looking for a chain here. We're looking at the fact that we've got an aromatic ring there that's the carboxyl group's bonded directly to, so we're looking at a benzoic acid in case B. Moving on to step 2, we're looking at the location and name of each substituent, counting the carbon as carbon number 1. For the straight chain, it's the carbon of the carboxyl group that's carbon number 1. For the benzoic acid, it's the carbon to which that carboxyl group's bonded in the ring that's carbon 1. So if we look at A first, we see that it's carbon 2 there, the alpha carbon, that bears that methyl group. So according to IUPAC, the name for that particular structure is 2-methylbutanoic acid. If we want to give the common name, it's alpha-methyl-butyric acid. So notice the difference. We use the number 2 in the IUPAC name, the alpha character for the common name, and we also change from butanoic for the 4-carbon chain in the IUPAC nomenclature scheme to butyric for the 4-carbon chain in the common naming scheme. If we take a look over at our benzoic acid, the only other substituent we have to worry about is that chloro group on carbon 3. Notice we count clockwise this time, because if we counted counterclockwise, we'd end up with a higher number there. It would be carbon 5, and we don't want that. We want the lowest possible number. So it's 3-chlorobenzoic acid would be the IUPAC name, or if you like your common names, and you will see them quite a bit, unfortunately, it's metachlorobenzoic acid. So just changing the number 3 to the prefix meta to go from the IUPAC to the common name here. I mentioned earlier in this lecture about alpha hydroxy acids, AHAs as they're commonly known. They occur naturally in fruit, milk, sugarcane. They're also used in skincare products, as I mentioned, and I think they're still fairly common in skincare products, again, until the next big fad wipes them out. But I think they've got some staying power because they actually do help remove that dead skin, and they're fairly gentle in doing so, so there's not a whole lot of drawbacks. There's that good activity of removing the dead skin, making the skin appear more vibrant and fresher. So they've withstood the test of time. As I said, they've been around for several years now, probably more than that as I get older here. And the sources, of course, glycolic acid. We looked at that last chapter on carbohydrates. That's from sugarcane, and so that's glucose that's been oxidized now to the carboxylic acid and has the hydroxyl group on that glycolic acid group there. The lactic acid comes from milk. That's what sours milk, actually. And then the other sources are all plant sources. We've got tartaric acid from grapes, malic acid from apples, and citric acid from citrus fruits. So fruit sources for those last three. Again, a plant source for the first one, sugarcane, for that 2-carbon, very simple alpha hydroxy acid. It only has an alpha carbon, so it's the simplest alpha hydroxy acid we can have. And then the sour milk there for the lactic acid. So there you have it. Take a look at your skincare products, see if you have any of these, and you'll probably be able to recognize the names now and even the sources. Let's go ahead and pause here for a learning check. We've done a lot with the IUPAC and common names for these carboxylic acids so far, and now it's your turn to see how well you understand those naming conventions. So we've got 3 structures here, and your task is to give both the IUPAC and common name for each of those structures. So please pause the video here while you complete that task. Start us back up once you're ready to check your work. Good luck. Okay, so hopefully you had fairly easy time with these. Notice we don't show the C double bond O in these particular abbreviated structures. That COOH is another way to show the carboxyl group to indicate that's a carboxylic acid. So for A, we have a 2-carbon carboxylic acid, no other substituents. That's good old ethanoic acid according to the IUPAC scheme, or as you'll more commonly see it, acetic acid, which is your principal acid in vinegar. Vinegar is a dilute solution of acetic acid. If you get the distilled white vinegar, it's just acetic acid and water, about 5% acetic acid, 95% water. For B, now we do have a substituent there. So this one's a 3-carbon chain with a obviously carbon 1 being the carboxyl group and then a substituent on carbon 2. So it's 2-methyl propanoic acid, or if you're using the non-IUPAC common scheme, we have alpha-methyl propionic acid. Notice we went from propanoic to propionic, and of course from 2 to alpha, going from IUPAC to common. And in the last case, we have a benzoic acid with a bromo group on carbon 2. So we have 2-bromobenzoic acid, or orthobromobenzoic acid, by the common naming scheme. So hopefully you were able to get both the IUPAC and common names correct. If you missed any of those, hopefully you missed the common names, because the IUPAC names are really what we're after, but you are going to see them probably see the common names even more than the IUPAC names, honestly, with these carboxylic acids. So hopefully you've got both down. If you're struggling, then guess what? We've got another learning check coming up. Okay, here it is. So hopefully you had an easy time with the last one, and you'll have an equally easy time with this learning check. But if not, if you struggled a bit with the last learning check, then here's your chance to put it all together, show you understand this stuff, because again, we've got 3 structures, and you're asked to give the IUPAC and common name for each of those structures. So please go ahead, pause the video while you complete that task, and start us back up when you're ready to check your work. Good luck. Okay, and there we have it. For A, it's just a simple straight chain alkane, 3 carbons, so it's a propanoic acid by IUPAC naming. Notice we don't put the 1 because it has to be carbon 1 that is the carboxylic acid group, so propanoic acid in the IUPAC nomenclature and propionic acid in the common naming scheme. So close but not quite the same between the IUPAC and common for a 3-carbon carboxylic acid. For B, we've got a substituent there, so we've got a 4-carbon carboxylic acid, so by IUPAC it's a butanoic acid, and then if we look, remembering that carbon 1 is the carboxylic acid carbon, we have a 3-methyl butanoic acid by IUPAC nomenclature rules. If we instead name that by common naming schemes, we would have beta-methyl butyric acid, right? Butane becomes butyr for the butyric acid, and that's the carbon of the carboxylic acid is the ipsius carbon, so the next carbon there would be the alpha, and the one that actually has the substituents one further away in the beta position, so beta-methyl butyric acid. Finally, for C, we've got a case where we have another benzoic acid. In this case, it's another example of a bromobenzoic acid, but in this particular example, we have the bromo on the position 3 of the benzene ring. So it's a 3-bromobenzoic acid by IUPAC's nomenclature rules, or a meta-bromobenzoic acid by the common naming scheme. So hopefully if you struggled in particular on the previous learning check, hopefully you were able to apply those skills and do very well on this learning check. Or even better, you did well on both learning checks and you've got the naming down very well. If unfortunately you're struggling with both learning checks and naming is really getting to you, please do reach out for some help. All right, so let's talk about the preparation of carboxylic acids. Carboxylic acids are generally prepared by oxidizing primary alcohols or aldehydes. We need that carboxylic acid carbon in position 1. That's why we're looking at primary alcohols or aldehydes, which already have a carbon-oxygen bond in position 1. Or more commonly from the oxidation of ethanol, which of course is a primary alcohol, which produces our good friend ethanoic acid or acetic acid, as it's more commonly known. So there we have ethanol itself, a primary alcohol or ethyl alcohol by the common naming scheme. Gentle oxidation to make the aldehyde ethanal or acid aldehyde as it's more commonly known. Of course, ethanal and ethanol would be the IUPAC names. Acid aldehyde and ethyl alcohol would be the common names. And then finally, under further oxidation, we get ethanoic acid, or more commonly known, acetic acid. And that's one way to know that things have gone a little sour, so to speak, right? Quite literally by the taste. but ethanol would be our wine component. And if your wine is subject to too much oxidation, you can have the wine go to vinegar, acetic acid. So that's a bad thing for wine drinkers. I don't have to tell you that, right? But that's where we get things like red wine vinegar or balsamic vinegar. It's by allowing those alcohol groups to get fully oxidized to carboxylic acids, and then as long as you're interested in it as vinegar, then it's not a problem, right? But if you're drinking it expecting it to be wine and you get that vinegar flavor, that's not so pleasant. Okay, so before we leave this first lecture in chapter 16 here on particularly the carboxylic acids, but also the esters that we'll get to later on, um, we have one final learning check. Which alcohol would be used to prepare the following? So for A, butanoic acid, what alcohol would it come from? And B, propanoic acid, which alcohol would that come from? Go ahead, stop the video here while you write those answers down, and then start us back up when you're ready to check your work. Good luck. Okay, so of course we needed primary alcohols to get to carboxylic acids. So strictly the question asked for the alcohol. So A would have been 1-butanol and B would have been 1-propanol. But of course, if you want to consider it as a two-step process, first those alcohols would respectively go to the aldehyde. So 1-butanol would oxidize to butanal and 1-propanol would oxidize to propanal. And then finally, under further oxidation, we would get the butanoic acid that we started with in A and the propanoic acid that we started with in B, and that's how we would take those final products and think backwards, do what we call retrosynthesis, go backwards to figure out what alcohol we must have started with. So hopefully you had butanol and propanol, and of course they had to be the primary alcohol, so it was strictly 1-butanol and 1-propanol. If you're struggling with that and how we approach that sort of problem, please do try some additional ones, and if it's still giving you trouble, don't hesitate to reach out to me. Otherwise, if things are going well, we'll see you in the next lecture.